Now recording. And Jordan just came in, right? Justin came in. You have 2 first names and 2 another. Okay. Anyone else? Let's see. I know I can't see the roll because of that. Sabrina, right? Okay. All right. Anyone else slip in while I wasn't paying attention? Okay, good deal. Okay. I was just saying my office hours are modified big time the rest of this week. Today, no change. 11:15 to 12:15 when I'm eating lunch, I eat in my office, so you're welcome to come. And then 2 o'clock until 4:45. Nothing changes there. Tomorrow, big changes. I will be flying to Dallas tomorrow afternoon, so my office hours, which are normally on Thursdays, 12:15 till 4:45, I will be either at the airport or taking off or something right about or on the way. Yeah, definitely at the airport by then, if we haven't left yet. And then on Friday, also, not be on the Birmingham campus, 7:45 to 11:45, which are my normal office hours. So Thursday, Friday, basically no office hours at all. Then next week, Monday is fine, no problem there. Tuesday, my office hours are shortened because I'm missing a class Thursday, tomorrow, that I'm going to make up for them on Tuesday. So we're going to have a double class then. So when it normally started at 12:15, it will now start at 1. The office hours will start at 1. So, but after that, we should be back to normal, whatever normal is. All right, let's get on with the slideshow. First thing I want to know if you have any questions on anything we've covered so far. And the other thing I'd announced earlier while I was waiting for the system to come up, everything is so slow today, is that, yes?
As far as our first test.
Yes.
When is that going to be?
Okay.
I know we're going over stuff, preparing us for it.
Right.
But can you narrow it down and say, this
Okay.
section right here will be on the test and all that kind of stuff, but we'll know exactly what to prepare for. Because we covered a lot of sections.
Right.
That,
Okay.
Introducing us to something we ain't going to do on the first test.
Okay. We're in 6.2 now. We're almost through. We should finish that if I can ever get the system to work. And then we'll move to 6.3, and then we do 6.4. When we finish 6.4, we're going to have the test. Okay? I was hoping that was going to be next Wednesday, but it looks like it's more likely the following Monday. Okay? So sorry that it was so late. Now, what's on there? A good indicator, not the same questions, good indicator. The first 3 sections we covered, your quiz, those are good samples of the type of things you'll be asked for. The next 3 sections, the one we're in now, 6.3 and 6.4, basically what your homework exercises are. That's your best thing to gauge by. Okay? And and if you have any questions on anything, ask them, and I'll try to clear those things up. Quiz questions, most of you have turned those in, or a good number of you have. But if you had questions about them, now I won't work the problem that's on the quiz, but find anything in the book, any of your homework exercises that are like the quiz question or things you think might be on the test, I'll be glad to work those anytime. Okay? Yes?
So the test going to be like the quiz, but just more problems.
Right. Actually, the quiz was 1 page, 10 questions.
Okay.
The test is going to be 2 pages, about 10 questions per page. It won't be exactly that, but something. The first page will be a lot like the quiz, not the same questions, but similar. And then the second page will be the new material. Yes?
It's not going to be the word problem.
Oh, we hope so.
But how many? Like seriously?
Oh, 15 or 20. No, I don't know. No. Don't sweat them. We practice doing them in class. Do them that way. Okay.
So pretty much we know section 3 in chapter 6.
The Anthony, right? Oh, I'm sorry. Say again? Yes, got it. Josh Brown. Got it. Yeah, I got to get out of that light. Got it. There you are. Okay, was there another question? I was blinded by the light. Okay. All right. All right. Was that all the question? I didn't know if there was one hanging. Okay. Where we left off last time, we were talking about good old problems, sometimes called word problems. There are two special kinds of right triangles that we use extensively in mathematics courses and in life in general. The first of these is the isosceles right triangle. Does anyone know what that means? The prefix iso. Does anyone know what that means? Okay. Any of you use topographic maps? You haven't? You have. What are those lines on a topographic map called? Do you have any idea? Isoclines. Okay? Have any of you ever seen a weather map? And they'll have the high pressure, like that big hurricane, what's his name? Not Michael. What is it? Matthew. If you look at that, there's circles around that, really dense circles around it. What those are isobars. Areas of equal elevation, areas of equal barometric pressure. Okay? So something that's equal. So an isosceles triangle, basically equal sides is what that means. Now, all sides equal? No. Two of the sides are equal. That's what an isosceles right triangle is. In which is a right triangle that has both legs the same length. Okay? Now, this is a right triangle, so we know the one angle is what? It's a right triangle. Say again? 90 degrees. And if the other two sides, the two legs are the same length, that means these two angles are the same. That's geometry, right? So the three angles of a triangle, any old triangle, three angles add up to 180. So if one of them is 90, these two are the same. What do those have to add up to? Add up to 90, and if they're the same, that means they're each 45. So that's what it is. A right triangle has both legs the same length, meaning both angles the same length. So sometimes we call it a 45, 45, 90 right triangle. Okay? Now the second special kind of triangle that we use frequently contains, again, the two angles have to be acute. Now what does that mean? Hair looks nice? No. What does that mean? Second, yeah, less than 90 degrees. So, of course, if one angle's 90, the other two have to be acute because they've got to be less than 90. And those two are the acute angles of 30 degrees and 60 degrees. Okay? 30, 60, 90, that's pretty evenly spaced and everything. Has some special characteristics of a 30, 60, 90 triangle also. If you've know anyone who's into drafting, as a drawing, mechanical drawings and stuff, generally they'll have at least two types of triangles on their drafting table there. One of them probably going to be a 45, 45, 90, and the other going to be a 30, 60, 90. There may be others, but those are almost always there. In such a right triangle, the 30, 60, 90 right triangle, the side, now here's the key here. All right. There we go. I'll draw it. Waving arms does so much, but, and guess what? The folks at home can't see the waving arms anyway, okay? But they can see here if anyone's watching at home. Let me get okay, where are there they are, okay. My keys down here. There we go. All right. So here we have our right angle, okay? And if it's a 30, 60, 90, I don't know if that's 30, 60, 90. Let's just imagine it is. There's your right angle. Which one would be 30? Which one would be 60? One at the top, one at the bottom. Which is 30, which is 60? Okay. The little angle is 30. Okay. The bigger angle is 60. And this one's 90. Right? Goes by size. Now, which side is the biggest side? The top, the left, or the bottom? Huh? The hypotenuse, exactly. And which one's that? Okay, yeah, this is hypotenuse. This is the longest. You can either call it H or you can call it C. You can call it hypotenuse. You can call it anything you want to. This is the longest side. Which is the shortest side? Okay, the vertical one. That's the shortest. I'll call it S for shortest. And then the middle side, of course, would be this one down here. Now let me suggest to you something, and this is true. The side the largest angle is the longest side. The smallest angle is the shortest side. Opposite the middle angle is the middle side. Okay? Now, what they're saying here is the side opposite the 30-degree angle is equal in length to 1/2 of the hypotenuse. That's amazing, isn't it? But that's a fact of geometry, and it's a fact of trigonometry. If it's a 30, 60, 90 triangle, this is exactly half of that. Now, mine's probably not exact, but you get the general idea. They are.
What's
Yes.
half of the hypotenuse?
1/2 of the hypotenuse. The short side on the 30, 60, 90 triangle is always 1/2 of the hypotenuse. Absolutely. That relationship, along with good old Pythagorean theorem, I think someone's already chosen that as a paper topic, haven't they? I saw it on some list, maybe it was the other class, or Pythagoras or something, provides us with another problem-solving technique. Okay? So we already know this is half of that. What would that leave this to be? Let's pick some numbers. What length do you want this side to be? 4. Okay, he likes big numbers. So if this is a 4, what would the hypotenuse have to be then? 8. You're very good. What would the middle side have to be? Hint. Pythagorean theorem. Okay? How does that read? You forgot this. Aha! So if we call this A, B, and C, see, I knew y'all were going to change on me, weren't you? Okay. A, B, and C. A squared plus B squared is equal to C squared. When is that true? Any right triangle. Not any triangle, but any right triangle, that's going to be true. Okay? Now, what is our A? The way we wrote it here? 4. 4 squared plus, we don't know B, so we'll leave that as B squared. Boy, this pen is so slow. Okay? Is equal to, we know C? 8. 8 squared. Okay? And what does that give us? What? 16 plus B squared is equal to 64. Okay? Then you could subtract 16, right, from both sides, and that gives you B squared is equal to 48. Excellent. And then you'd have to do the square root of 48. Now, that's not a perfect square. It does contain a perfect square. What perfect square do you find in 48? Any perfect squares living there? 4, certainly. So we could factor out a 4. So what would B be? I sort of left this one off. What's the next step here? I got ahead of myself. How do you undo a square? Square root, so that would be the square root of 48. And this is where we start looking for perfect squares. We found that's the square root of 4 times the square root of what? 12. Okay, square root of 4 is 2. Oh, I left off my plus minus, didn't I? I should have done that, shouldn't I? Except what are we dealing with? Lengths of a side. Draw me a triangle with a -4 length. Can't do it. Lengths are positive, okay? So that's why I left off the plus or minus. Most of the time you do put that in. How about 12? Does that have any perfect squares living in it? 4 again. So this will be the square root of 4 times the square root of 3. Okay? Well, square root of 4 again is 2. Okay? So 2 times 2 is 4. This pen is so slow. 4 root 3. That's what your B is. Hey, wait a minute. The short side is 4, and the middle side is root 3 times 4. It's always going to be true. The long side, the hypotenuse is twice this. The middle side is always root 3 times the short side. So there's another characteristic. That relationship gives you this technique. Okay, let's see. I can't remember if they do this on this page or not. No. So here's example 11. They skip, well, wait a minute. They skip 10. So let's do 10 first, and then we'll do 11. We'll do 10 on this page, then we'll come back and do 11. Find the length of each leg of an isosceles right triangle that has a hypotenuse length of 5 meters. How would you do that? Okay, I'm going to write it out sort of. Find the length of each leg of an isosceles right triangle, that's triangle, okay, that has a hypotenuse of length 5 meters. Okay. How would you work that problem? It's one of those fun word problems. We love them. Okay? How would we do it? First step. Draw a picture. I love it. I love it. I love it. Okay? So we need to draw a picture of what? A what? A triangle. Any special triangle? A right triangle, so we want a right angle in there. And what's special about this right triangle? It's an isosceles right triangle. What does that mean? Oh, how quickly we forget. Say again? Yes, these two legs are equal to each other. And I tried to draw them as close to that as I could, and that means the hypotenuse is where? Connecting the end. Okay? And what did they tell us? Hypotenuse was 5 meters. See, that picture is worth thousands of words, isn't it? Okay? Now, we know those two lengths are the same. Here's a little trick they use in geometry and trig. I'm going to put the single tick mark through those, meaning they're the same length. Okay? That's what we're looking for. Find the length of each of those legs. Okay, and you do that based on? Okay, wait. That was the 30, 60, 90. This is the 45, 45, 90. This is isosceles, not the 30, 60. Okay? Good try, though. Okay? What do we know about these two sides? What did the problem tell us? Isosceles, they are the same length. So rather than call them A and B, we can call them A and A, right? Okay? So they got the same length. A, my brother Daryl, my other brother Daryl. Okay? And this is going to be C. So good old Pythagorean theorem tells us what? A squared plus A squared equal what? 5 squared. Okay? It's 5 meters squared. I left off my unit, but please forgive me. Okay, what do we do with that? Combine like terms. And what does that give us? Say again? How many A squareds you got? 2. 2 A squareds. It's equal to, what's 5 squared? 25. And then what do we do? Say again? We want to isolate the A. That's what we're looking for. Divide by 2. Okay? And that will give us A squared is equal to Anyone do that quickly? 12.5. Good. Now what would you have to do? To find A? How do you undo a square? Take a square root. So A is equal to the square root of 12.5. Now 12.5 doesn't have any hidden perfect squares in it. 12 doesn't, 12.5 doesn't. So you just have to use a calculator to see what it is. Now, should I put plus or minus here? No, because this is the length of a triangle. We're only looking for the positive side. So you just plug that in the calculator. That's how long it is in meters. And that's something between, can you give me the two integers that's between that answer? 12.5 is between what two integers? Second? Okay, the 12.5 is. The square root of 12.5 is between what two integers? Find the perfect square less than 12. Y'all know your perfect squares, right? You did a table a long time ago, right? Perfect square less than 12. Bigger. 9, okay? Square root of 9 is? Second? 3, okay? What's this? A perfect square greater than 12.5? 16. And what's this? Square root. 4. So there you have it. Something between 3 and 4. Punch it down with your calculator, see what you get. Square root of 12.5. 3.6. Something like that. I'm guessing. Now, phones don't usually do square roots too well. I don't know. Yours might. My phone doesn't even ring. No one has a calculator. Okay, let me say this, folks. You can use calculators on the test. Hint, hint. Okay? I don't have but a couple that... All right, 3.5. I was guessing 3.6. Okay, that's about the length of that. Not 2 or 2.5 or something like that. Yeah, about 3.5. And that sort of makes sense. Let's see what they got in the book. Oh, they wrote it as 5 root 2 over 2 meters long. Oh, that's how I have that on my measuring tape. Okay. It's amazing. So anyway, that's a weird way to express the answer. All right, oops. Here is example 11. I've got to do this first, sorry. Was there any questions on this before I erase it? Well, I can't get this to work. Okay, let me try it this way. All right, can I erase it? Okay. Here's example 11, next page, 308. Suppose that a 20-foot ladder is leaning against a building and makes an angle of 60 degrees with the ground. How far up the building does the top of the ladder reach? How would you approach this problem? Say again? I can't hear you.
Is this the one we just did?
No, well, this was on the page. I did the one before this. They didn't have a slide of the one before. I wrote it underneath it. Okay, but this one's this is 11. That was 10. How would you approach this problem? Draw a picture. Great, fantastic. And what do you need to put in the picture? You tell me. A what? A ladder, okay? Before I draw the ladder, I want to draw some ground here, okay? And let's assume that's pretty level, okay? And what do I need also? A what? Okay, maybe a building. Okay, there's my building, okay? Now, where do you want to draw the ladder? Against the side of the building, right? Now, the thing to remember, I'm going to put it like that in hopes I got it close to right. There's my ladder, okay? Suppose that a 20-foot ladder, what does that tell you? of what? The ladder. But there's the ladder. Now, I'm going to make an assumption here, folks. I hope it's a pretty good assumption. I'm assuming the building is a straight building, okay? Not the leaning tower piece. If we were there, we're in serious trouble, okay? We're not. We're not in Italy. We're in, okay. So our building is at a right angle. And we're assuming that it's level ground. Remember I said that. So there's a right angle, okay? Now, this 20-foot ladder, with that right angle, how would you describe, where is the 20-foot ladder relative to that angle? And that's a right angle. Where's the ladder? It's the hypotenuse. So there's your 20-foot ladder, okay? That's the hypotenuse of that angle, that triangle. It's leaning against the building and makes a 60-degree angle with the ground. Now, that tells you what? Where's your 60-degree angle? That one up top or that one at the bottom? The bottom, of course. There's the ground, so it's a 60-degree angle here. So this is a 60-degree angle here. And by the way, that makes this one up here a 30-degree angle. Very good, because that has to be 90. That's what it means to be a right angle and a right triangle. Okay. Just with that, there's not much we can do with the problem. We've written down everything they told us. Oh, one thing. How far up the building does the top of the ladder go? What are we looking for here? You'd think so. I'm going to call that H if that's okay with you. You think that H is 20 feet? Can't be, because this is 20 feet. And that has to be something a little bit less than 20. Now, if you put the ladder smack up against the building, it would be 20 feet. You going to climb it? No, not me either. Okay. Nowhere close. In fact, you're going to have sort of a hard time getting me going up a 60-degree angle. I might, you know. I ain't going to go up one that's nuts. Okay, say again?
I said straight up and down.
Yeah, that ain't going to work for me. Okay. So we know the one thing we're looking for is how far up the building. I put H. If you want to use something else, you can use it. Would you rather use B or something else? I don't care. Tell me what you want to use that. So H is fine, okay? That's a good thing to do. How far up the building does the top of the ladder reach? That's your question. Make that your variable. Because when you solve the equation, you're going to have the answer to your question, right? So we're looking for H. There it is. Okay. How are we going to calculate what that is? And again, with what they've given us in the problem, that's it, folks. Do you know anything else that you could use to help solve this problem? You tried it before with a 45. Didn't work there, but this is a 30, 60, 90. What do you know? Which one is? The short side. Which is the short side? One on the ground there. So that would be how long? 10 feet. Can we solve this problem? Yes. How? Pythagorean theorem. And how would that go in this problem? Help me, help me. 10 squared plus H squared, 20 squared. Look at you. You got it done almost. Well, we just have to do the math. What does that do? 100 plus H squared equal 400. Okay, what do we do next? Subtract 100 from both sides. And that would be H squared is equal to 300. And what would you do then? Take a square root. That gives you H equal. Do you need plus or minus? No, because this building isn't downstairs. No, it's not underground. Okay, so this will be square root of 300. And you could do the things we were talking about before, and probably I'll take you through that. But we'll wait and do that in the right chapter. All you have to do is plug this into a calculator. But none of you have a calculator, huh? Okay, hang on. I'm hanging by the thread here.
Are there certain limits on the calculator? Can we use any kind of calculator, or do you kind of,
Pardon me?
can we use any kind of calculator, or does it have to be a plain basic calculator?
I don't care what kind it is. If you bring in a McRae supercomputer, I'll probably object because it's going to take up too much room. But, yeah.
17 point.
Say again, 15 point something? 17.3? It says to the nearest tenth of a foot, and that would be feet. So you can go up, guess what? I ain't going up 17.3. I'll make it 17.2, whatever, That's to the nearest foot. Let's see. Okay, any questions on this before I delete it? We'll get to see their picture. It's not going to be as pretty as mine, but okay, you okay with that? All right. Here we go. Almost as nice as mine. There's the ladder, 20 feet, going up the building. And we notice here, because this is a 30, 60, 90 triangle, you know this is 10 feet down here. Just like you said. And when you're looking for H, that's what we had. I drew it over here because it makes more sense over there. But that's how far up the building it goes. And there's your picture. All the information is given. Use Pythagorean theorem. 8 squared plus 10 squared equal 20 squared. That's fine to write it that way. And that would be h squared plus 100 is 400. So h squared is 300. Taking the square root, about 17.3 feet to the nearest. That's to the nearest tenth of a foot. It touches the building at a point approximately 17.3 feet from the ground. The reason I say approximately, these irrational numbers, they're never exact, so you have to just round them to something. Does that make sense? Just what you got. All right. Concept quiz, bottom of page 308. A very good thing to review to make sure you got the concepts down. It's true, false. Don't expect many true, false on the test, but I think this would clear your mind into thinking a little bit. Now let's do homework exercises. Some of the odds 1 through 19. Remember, probably something on your test. I can't say for sure. It's going to look like some of these problems. Let me give you. I think I backed off of that. I said 1 through 11, I believe before. No, 1 through 13. No, I think 1 through 19. Yeah, I think you can do all those. Okay. Skip 21 to 25, even though we did one like it in class. Jackson's not here to explain it to us, but we did. And then for the next group, here are the ones I'd suggest you do. 27, 45, 47, 51, 59, okay, and then in the next group, 67. Very good, you remembered well, okay? And then in the next group, really there's none of those we can do exactly, but you can use your calculator and do them. So you can do either of those if you want to, but don't feel obligated to. Same thing with the next group. I'll back off that a little bit. You can do C in 73. You can do A in 75.
Where is it?
This is top of page 310. Okay? You can do one part of 73 and one part. You can do them all, but that come out without round off and radicals would be 73, one part of that, and one part of 75. The rest of them, don't worry about too much. 81, I think you can do. So do 81. No, I'm sorry. You can try it if you want to. Okay. Yeah. Most of those are going to require radicals, and I'm not going to test you on radicals. Okay. So let's move on to, let's see what's next. Okay. Goodness, my head's clogging up. Well, There we go. It sure is slow today. But I'm slow too. I'm old. Yes. There we go. Let's move on to 6.3. Wish I were that tall. Okay. It'll get there one of these days. Maybe. I can't see it's doing anything but sitting here quivering. So I'm going to hit it again. There we go. Something's happening. It's trying to do something. Here we go, maybe. Yes. PowerPoint takes so long to open. I love Microsoft products, though. Yes, I do. So, it will open one of these days. La-di-da. Here we go, maybe. Okay. Is it down here? Not yet. I keep thinking. Well, I can't see anything there yet. It says it's there, but it's not showing up. Oh, here, wait. Here we see. Nope, that's not it. I'm going to try it again. 6.3. It's probably just going to confuse it, but I love technology. It makes life so much easier. No, it really does, but it's just sometimes it's woefully slow. Here we go. Got it. Okay. So let's go from current slide. I appreciate they've got all these here for me. I don't have to write all this, but still painted in that. Okay. Some other body parts. Quadratic equations and inequalities. We're basically going to stick with mostly equations. 6.3 is completing the square. And of all the ways to solve quadratic equations, this is, I shouldn't say this, I know. This is probably my least favorite. But guess what, folks? You need to know it. Number one, it's going to get you to a really handy way to do it. But without knowing this, you can't get to the next. But on the other hand, this is the only time in math you're going to need completing the square. So we need to go over it. It's just not always the most fun. All right, so we will solve quadratic equations by completing the square. We have solved quadratic equations by factoring and applying the zero product principle. And then if we can set everything equal to some expression squared is equal to some numerical value, then we can do it that way. Okay, we did that in the last section. The, factoring in chapter 3 and in the last section. And then we introduce this lesson. In this section, we examine another method called completing the square, which will give us the power to solve any quadratic equation. It's not one that you can necessarily get into this form. Actually, we're going to kind of get it into that form and then make it work. Okay? A factoring technique that we studied relied on recognizing a perfect square trinomial. Does anyone remember what they look like? Perfect square trinomials. I know it was weeks ago, so who could remember anything that long? Especially since you're going to be tested on it. Okay, never mind. Okay, perfect square trinomial. How does that look? Trinomial, 3 terms. What's about the first term? Perfect square. How about the last term? Perfect square. Okay, you got it. How about the term in between? It could be a plus or minus, you're right. It's twice the product of the square roots of these two. Remember that? When you FOIL that, you get twice the cross product. That's going to be what a perfect square trinomial looks like. We're going to use perfect square trinomials to do this. So in each of the following, what is the square of that? x minus 4, x plus 4 squared. Square the first, x squared. Square, now let's see. Do the middle part. What did I just say? Twice the product of the two. What's the product of those two entities? Okay, 8x. The product is 4x, double that is 8x, and then
16.
plus 16. How about this one?
X squared.
X squared.
And plus minus 6x squared would be 30.
Don't square it, double it.
Double it. That'd be 12x.
Minus 12x, perfect. Now double, now square it.
9 would be 36.
Plus 36, good. Remember these are always pluses here. How about that?
X squared.
X squared.
And double it. That'd be ax squared.
Now ax squared.
2x.
Plus 2ax, got it? Anyone can answer? I hear a lone voice out in the wilderness there. What's the last term? A squared plus a squared, always plus. Note that in each of these squared trinomials, the constant term strange way to say it, but it's true. The constant term here is half of this, the coefficient here. 16 is half of 8, which is 4 squared. 36 is half of minus 12, which is minus 6 squared, 36. A squared is half of 2a, that's your constant. Half of 2a is a squared. Okay, now the reason they're saying it's so convolutedly backwards there, that's how we're going to do completing a square. That's going to be the big deal for us. So you take half of this term and square it to complete the square. That's what you do, half of the coefficient square. That relationship enables us to form a perfect square trinomial from any trinomial you have by adding the proper constant term. And we want the proper constant term, don't we? So to find the constant term, take 1/2 of the coefficient of the linear term, the x term, and square that answer. For example, what if you wanted to make a perfect square trinomial out of this? What would you have to add to it? Take half of 10, that would be 5, and square. And that would give you 25. All right, I feel like a dentist here. Okay, the coefficient of the x term, or the linear term, is 10. Half of 10 is 5. 5 squared is 25. That would make that a perfect square trinomial. So the perfect square trinomial that can be formed from that expression is this one. And that perfect square trinomial, what would be the binomial is the perfect square of? Yeah, that would make that when you square it, you get that. X plus 5, you got it. X plus 5 squared. Now here's the little hint that I do when I'm doing this. If I were trying to make this a thing, when I take half of this, I'd write down x plus 5 right there. Half of 10 is 5. Square root of this is x. Keep the sign. That's going to be the thing. When you square it and do that other, that's going to be the binomial. So write it as you do it. I do anyway. All right. So let's do this one. Now they didn't show us how to do this. I'm going to show you how. All right. I've got to get my pen back. Okay. Now I'm going to rewrite this. X squared plus 10x blank minus 2 equal 0. Okay? That's the same thing. It's just got a big blank in there, right? Agree?
Yes.
Okay, we're going to complete the square. Notice I kept the terms with x in it sort of separated off the terms without x in it. Okay? Now, how do I complete the square? Should look pretty familiar. Take half of that and square it and add 25. So when I take half of that, like I said before, I know what's coming next, so I'm going to write x plus 5. Okay? I know it's going to be a square because that's what we're doing. Half of 10 is 5. Square 5, you get plus 25. Is that the same equation we had before? Why not? Because you added 25. So what must we do to be fair about it? If we add 25 to the left, you better add 25 to the right. You got it. Okay? So now we have x plus 5 squared minus 2 equal 25. That is the same equation we have up there. It just looks different. Right? Because this thing right here is your x plus 5 squared. Here's your minus 2. Because you added 25 here, you have to add 25 there. You get 25. So what might we do next? Add 2 to both sides. Add 2 to both sides to get rid of the minus 2. I like your way of thinking. Okay? So this gives me x plus 5 squared is equal to, those go away. Second? 27. Now guess what we might do then? You've got a perfect square here equal to a number there. Take a square root of both sides. That's it. And what does a square root of the left-hand side give you? Well, let's just write them in. Okay? Now, we're not dealing with lengths of triangles anymore, so what did you better do on that right-hand square root? Plus or minus, you got it. Plus or minus root 27. What's the square root of a square? Square root undoes the square, leaving you with x plus 5. You got it. The square root undoes the square, leaves you x plus 5. And this is equal to plus or minus the square root of 27. Now, say again? Yes, that has a 9 times 3. Okay? Square root of 9 is 3. So this gives you x plus 5, goodness gracious, is equal to plus or minus 3 root 3. Okay? And then to solve for x, you just subtract 5 from both sides. So I would write this as x is equal to negative 5 plus or minus 3 root 3. Now again, that has radicals in it, so don't feel too thing. Once we do chapter 5, we'll know how to do this better. But that is the answer I think they're going to have in the book. Any questions before I erase this? Yes? Okay. Okay, this one right here? Okay, first thing I did was leave a blank here after the 10x. All I did was split the 2 off here, and that gave me x squared plus 10x minus 2 is equal to 0. Same thing we had here, just with a blank in it. Okay? Then, what we did here was take half of this, the coefficient here, half of 10 is 5. When I got that, I just wrote down 5 here. I knew that was coming. You don't have to do it yet, that's what I do. Okay? Then I squared the 5, and that gave me 25. Well, I just added 25 to this side. I've got to be equal about it and add 25 over there as well, right? That's the same equation, it just looks different. Looks a little worse. Now, what we did here, this is a perfect square trinomial, and we know it's the perfect square of that binomial square. Because that's how it works. You know, whatever half of this was, that's what goes in the binomial. The square root of this, and notice this is the square root of that, and this is twice the product of that. So this is the binomial squared. Minus 2 equals 25. 0 plus 25 is 25. Then I have a perfect square with something added, subtracted from it, so add it to both sides. And that put it there. And that gave us a perfect squared. X plus 5 squared is equal to 27. and then we undo that by taking the square root. Plus or minus. Remember here, this is the math part. This isn't physical quantities anymore. It's actually, so you have to include the plus or minus. And that gives you the answer. Now, if you wanted a decimal answer, here's what you do. Minus 5 plus 3 times the square root of 3. That gives you one answer. Minus 5 minus 3 times the square root of 3, that gives you the other answer. You get two answers, one of them with the plus and one with the minus. The minus 5 is the same in both, but you're adding something to it or subtracting something from it. Okay? Does that kind of make sense? Okay. Does that answer your question? All right, good. Any other questions? All right, let's clear that out of the way, and let's see how they did it. Okay, they wrote down the question without putting a blank in it. And here's the other thing you can do. They do it this way. This is perfectly fine, too. They added 2 at this stage. They should have left a blank there, but it comes out the same thing. If I were writing this and adding 2 to both sides, I'd have put equal 2 over here, so I have a blank to work with. But they're going to insert the blank next time. They're going to do half of 10 is 5, just like we did. Square 5 is 25, so they're going to add a 25 to the left and add a 25 to the right. Same thing we did. We just did the plus 2 later, okay? But we get the same thing. X plus 5 squared is equal to 27. Exactly the same thing we did. Now we take the square root of both sides. X plus 5 is equal plus or minus root 27. And they factored out a 9 just like David did and made that plus or minus 3 root 3. And let's see, they subtracted 5 from both sides. So they wrote the solution set this way, or you could have actually calculated what they are. Okay? I hear some rumbling around going on. Is that indicating anything? How are we doing on time? 3 minutes? Oh, we got plenty of time here, okay? All right. Let's see what we can do here. That was example 1. The method for completing the square involves a quadratic equation is merely what the name implies. You complete the square on the variable part and add the numbers on the number part. Perfect square trinomial is formed, then the equation can be changed to the necessary form of x squared equal to a. Now rather x is an expression of x, and then take the plus or minus square root of both sides. That relationship for a perfect square trinomial, it states that the constant term is equal to the square of 1/2 of the coefficient. Holds only if the coefficient of x squared is 1. If the coefficient of x squared is not 1, you've got to divide by that. Okay? We'll get into that later. Okay? And show some examples of it as well. I think what they do, they skip a bunch of examples. Yuck! They skip all the rest of the examples. So where we'll start next time, they are really cheating on this one. We'll start with example 2, okay? That one doesn't have an A in it, but we will do that. So let's see if there's any homework problems in this set that you can work on. This is a really short section, by the way. I think you can do number 1, number 3, number 5, number 7, number 9, number 11, and let's see. Stop at 7. Stop at 7. Well, stop at 5. 1 through 5. Odd numbers 1 through 5. We'll do the rest of the rows next time. Good deal. Did I use most of the 3 minutes? All right. Good deal. Have a good weekend. If you need me tomorrow or Friday, I ain't going to be here, so wait till Monday. But if you catch me today, I'll be here till 4:45 today. Good deal. And by the way, folks, please get your quizzes in and your papers in if you can. Quizzes are really important. Good deal. Thank you so much. Excellent. gonna leave home without it, huh? Oh no, I can just give that good score to anybody. Okay.
Probably could.
Some of them may not want it. Is that what you're gonna say? Okay.
No, it's 100.
Oh, is it? Okay. Well, he's already graded it for me. That is so nice. I don't in here. The ones I had here just don't work. Either the outer staples or the jammed or something. Yeah, have a good weekend. Let me shut down Screencast-O-Matic here.